So let's start with this data organization in the memory and how do we access data uh, from various parts of a processor. There can be many different ways of doing things in a different way. One area definitely, how are we going to uh, arrange the information, multi-byte information in a byte addressable memory. We don't face this problem in our projects and with related to this CS147 DV because there we assumed our memory is word addressable. That means we are operating on word type of data only. If you recall, we don't have anything like load byte or load half word, that kind of instruction in our list of instruction in the CS147 DV set, right? We kind of knowingly avoided it, okay, just to keep our life simple, keep our circuit simple, and project to be done in a classroom environment. But in real life, your memories are byte addressable. Like means each address points to one single byte. It gives the additional challenge of how we are going to store multi-byte data. Definitely a word is a multi-byte data. A word is like 4 byte. Half word is 2 byte, right? How we are going to access it, right? So one way we can think of that, okay, let's say address 0000, we are storing this data in hex 480108F5, and memory address 4 we are storing the data 8228E58D, right? Then one way we can actually store it like, okay, starting from that memory address 0, we keep 48, which is 1 byte, right? So if you look at this number 480108F5, this hex is a multi-byte and there are 4 bytes. It is 48 is 1 byte, 01 is another byte, 08 is another byte, and F5 is another byte. So we start from the address 00, the next address where I store 48, and the next address I store 01, next address I store 08, and next address I store F5, and that's next address in the increasing order. I mean, starting from 000, I go next address is 001, then next address is 002, next address is 003. So that contains my this 4 address location now start containing my data 480108F5. Similarly, in the memory address 4, we can store 8228E5D8, starting from address 4 as 82, then 28, then E5, then 80 in the increasing order of the memory. Then, if we access a memory location 001 with a full word, of course, right? Then what we access? We access 01, 08, F5, 82. Of course, if you recall your CS47 or equivalent assembly language programming, there is a interesting problem of memory alignment. Like example, this 0001, this address is not really word aligned memory address, and possibly real system will actually give you an error there. It will send an interrupt, it will halt its process, stuff like that. So those things are there still, but right now we are making our life simple, assuming that, well, we can access word from any address. So we are trying to access it from address 1, and then it will be 4 byte from that address in the increasing order. So we do 01, 08, F5, 82. That's the content I'm going to access. Now the question becomes, there is an alternate arrangement as well, and is that arrangement wrong, right? For example, you have seen this from increasing order of memory address. We are storing 480108F5, right? What if we actually store it in a reverse order? Means lower address contains the lower byte and higher address contains the higher byte. So in the previous example, this specific example in this page 9, we are showing that our lower address contains the higher byte, like 48 is the most significant byte area and F5 is the least significant byte area. So as we go increasing order of the address, we are going from most significant byte to the least significant byte in that order, right? The other way would be is exactly the reverse direction. With the increasing order of the address, if I place the least significant byte at the lower address and most significant byte at a higher address, that's also a possible solution. And point is, it is not wrong, right? We can arrange it in that way. So these two classes of arranging data is known as big endian and little endian, where big endian given a memory address, so forget about that, okay, we store certain values there. Let's say arbitrary a memory chunk with an increasing order of address contain 480108F5. So for the big endian, which is assume the lower address contains the higher byte. Okay, so that way it becomes like 480108F5. This chunk is interpreted in big endian system as 480108F5, whereas the little endian system assumes that lower address contains lower byte. So your interpretation of this chunk of memory in the increasing order of the memory address from down to high is F5, which is the higher address, higher like significance position. So F5, we start with MSB for the highest memory address and then 080148. So our reading order is different, and which is not wrong at all, right? So there are two classic class of debate, like some prefer big endian, some prefer little endian. No one is wrong, but point is that once we start constructing a microprocessor, we need to be fixed on one specific system. Okay, depending on that, your memory access and connection to the memory actually depends on this, how you are going to take the data inside the register file and so on and so forth. So we can debate upfront before we fix our assumption whether big endian, little endian. But once we decide on one system, to follow one system, either big endian or little endian, we need to stick to that. Your hardware is going to be affected by this. Your software, this compiler and assembler side, is also affected by that assumption. So other thing interesting is the operand addressing modes. Okay, so operands can be two places, right? Even in our simple system. One is at register file and other is at memory. Also a third location is of course it is embedded inside the machine code, which is like I type of instruction, immediate type of instruction. So that immediate type instructions, that addressing type of addressing is called the immediate addressing, where your operand is a part of the machine code itself. Then direct addressing is that you are embedding address of the operand. So address as in the memory, address of the operand in your machine code. Okay. So we don't have that example in the CS147 DV or neither in the MIPS, but x86 style of assembly language has this type of addressing there, where you are embedding your memory address directly onto the machine code. Okay, and then you are accessing that corresponding address in the memory to retrieve the operand. Okay. Now indirect addressing is basically similar to direct addressing, but it has a two-step memory access process. So what is that? Your machine code embeds one specific address. Okay. So to access your operand, what processor need to do is first access the address which is embedded in the machine code, and then use that value as another address to access another memory location to get a real operand value. So this is an indirect method. So if you are familiar with the C language, it is basically a pointer to pointer kind of concept. Okay, a pointer variable pointing to another pointer variable. So this is your indirect addressing, whereas C language equivalent for the direct addressing is a pointer type variable. So if you are familiar with that, if you are not familiar with C, probably it won't make sense to you that point. But concept should be very clear, where your direct addressing is embedding the address of the operand in the memory directly into the machine code, whereas indirect addressing embeds the address of the operand, address of the operand. Okay, that's the indirect addressing. Now register addressing is what? Like your operand is directly, you can access from the register file. That's a register addressing. Of course, in CS147 DV, your most of the instruction has this register addressing, either in terms of your reading from the register file or writing from the register file. So you just pick up any example from CS147 DV and you can actually inspect that many of them are register addressing type, where your register number is embedded in your machine code and that operand being accessed from that corresponding register in the register file. Now register indirect is a very similar to your indirect addressing, where you are embedding your register reference into the machine code, and that register file at that register contains the address of the operand in the memory. Okay, so it's a pointer to pointer, one pointer being at the register file, other pointer as being memory, just in terms of C language, if you can think of that way. So register indirect is that your machine code is embedding a register value or register number. Okay, then processor will access that register file. That content of that specific register is another address. Then processor will access memory with that address to retrieve the operand. So that's register indirect. Then we have displacement, also CS147, especially DV, that instruction set has displacement example for load word and store word. So this is a relative addressing, displacement addressing with the offset, like different names can be placed there. But the idea is that you are defining both register, reference to the register, means which register to access, number of that register, and then offset. This offset can be a negative or positive offset. So what happens that when executing and accessing that operand, you are basically accessing first the register. You means the processor will first access the register file to retrieve the content of the register, that register reference being embedded in the machine code. Okay, so that register is accessed, and the value itself is an address, but that we call it a base address. So with that base address, we add the offset value, which is also a part of the machine code. Okay, a part of that machine code is the offset values, and that can be positive or negative. So with respect to the base address, now we can access either a positive value added on top of that address or a negative value added on top of that address. Negative value added means a value subtracted, right? And that gives you effectively your final address in the memory where your operand lies. You go and access that memory address, which is computed from the content of the register and the offset. You add them together. And then we have the stack. Of course, we have in CS147 DV, we have added this push and pop. That is a stack access. So it is kind of implicit, like there is no your machine code doesn't need a reference to where from your data or operand need to be accessed. It is always top of the stack. That's always assumed in that push and pop kind of instruction. So that's a stack addressing mode.